students. So far in the chapter of trigonometric function, we dealt with the trigonometric equation and their solution. Trigonometric equations and their solution. In the solutions, we have seen first is principal solution, and general solution. And now we are going to deal with solution of triangle. Solution of triangle is also known as solving triangle. Solving triangles means what? To find out unknowns. That is, to find out unknowns. Now, unknown means what? In a triangle, what could be the compounds of triangle? There will be three sides and three angles. Now, to find out three sides and three angles, okay, some should be known and some should be unknowns that we have to find out. So, three sides and three angles. So, to find out unknown elements, okay, only having information about angles, we cannot solve it. We need at least information about one side. So, at least one side should be given, okay, along with information of angles. Okay. That means it cannot be done if only information about angle, that means measure of angles are given and none of the side is given. So we at least need one side, length of one side is needed. Then only we can solve the unknowns of the triangle. There are some rules or theorems, we can say, which we are going to prove for solving triangles. The rules are the sine rule, cosine rule, projection rule. These are the three rules or the theorems we are going to prove. Before that, we need some results which we will be using in the solving of these rules. The result is the relation between area of triangle and circumradius of triangle. So this result we need to use in the sine rule. Okay. So now, what is circumradius? We have done this in the school level, but we will just recall this. What is circumradius? We know that circumcircle of the triangle. First draw a circle. Suppose this is the circle and a triangle. Obviously, first we draw a triangle while drawing the geometry of this circumcircle. Okay, circle passing through three vertices of the triangle. okay, is a circumcircle of that triangle. And what is circumradius? Suppose this is the center of that circle. We'll name the points A, B, C. Now, if we draw a diameter through vertex A, diameter obviously passing through the center of circle, then this radius, so this is O D, the radius OD OA is circumradius. Okay, you can say length OA also, and this is circumradius. Circumradius of circle of triangle ABC is denoted by capital R, and we will assume the area of triangle ABC as capital A. Okay, this will be our notation. Now we will prove the relation between area of triangle, that is A, and circumradius of triangle, that is R. Okay, that we have to prove the relation will be R is equal to ABC upon 4A. Now what are the ABC? ABC, we know that the length of the sides of the triangle, okay, denoted by, if this is vertex A, then the opposite side BC is denoted by A, small a, that is the length of BC is A. AC, length of AC is B, length of AB is C, that we will write over here, length of AB, C, length of BC, A, and length of AC is equal to B. These are the notations. Now we will start proof of the result. And for that we will put perpendicular from A on base BC. We will name it E. Hence AE is the height of a triangle. We will complete length AD to get a triangle ABD. Now, in triangle ABD and triangle AEC, we will find the similarities in the triangles. Now look at the angles. Angle ACB and angle ADB. Okay. In triangle ABD, the angle ADB, and in triangle AEC, the angle ACE. Okay. If we extend this E over here, we get angle ACB. Okay. So I'll write first over here that major angle ACE is equal to major angle ACD. Okay, you can see the geometry of these angles ACE and extended till B. Okay, so these are the same angle. Okay, now look into the triangle ABD and in triangle AEC, major angle ADB is congruent to major angle ACE. Okay, I'll write angle ACE instead of ACB. Now what is the reason? See, both the angles are subscribed by the same arc AB. Okay, arc AB. Okay. So we'll write the reason over here. Angle subscribed by same arc. Okay. Now another angle. Now look at angle ABT. What can you say about the measure of this angle? We know that OD is the circumradius. How it came? When we draw diameter AD. So if AD is the diameter, the angle ABD is in the semicircle. So angle inscribed in the semicircle measures 90 degree. So first we write major angle ABD is equal to 90 degree. The reason is angle inscribed in semicircle. Now therefore angle ABD is congruent to angle AEC. See, A is the perpendicular we have drawn in the geometry, so AEC is also 90 degree. Therefore major angle ABD is congruent to major angle AEC. Therefore these two triangles are similar by angle test. Now since this triangle are similar, the corresponding sides are in the ratio. So we'll write AD upon AB is equal to AC upon AE. These are the corresponding sides of similar triangle, or you can write by similarity of triangle. This also you can write. Okay. Now if you see AD is the diameter, okay, and OD is the radius. So circumradius you have denoted it by R. So if OD is R, then AD will be 2 times R. AB and AB we have considered as small c is equal to AC. AC we have considered as small b, and AE is the height of the triangle. We will consider it as small h, height of the triangle. Now we need to find out this value of h, as h is considered as the height of the triangle ABC. So we will use area of triangle ABC. This is notation for area of triangle ABC. We know that it is half into base into height. Half into base is BC, okay, which is nothing but length A. Length of BC is A. Into height we have considered as h. So this is nothing but A into h upon 2. So we will replace this value of angle area of triangle ABC into the equation. How? We have considered area of triangle ABC as capital A. So we will write this as capital A. We'll transfer the values to A upon A is equal to H. Now we will replace this H into our equation. So we get 2R on C is equal to B upon value of H is 2A upon A. Now this A, small a in the denominator, okay, will go in the numerator as it is the denominator of a denominator. Okay. We will transfer this C over here. So we got 2R is equal to this C is transferred over here. This A will come into the numerator, A, B, C upon 2A. So we are going to use this form into the sine rule, and the relation between the circumradius and area of triangle is defined as R is equal to A, B, C upon C. This 2 has been transferred over here, so it will come in the multiplication with this 2. 2 into 2 will be 4. A stands for area of triangle. Okay. So this is the required relation between circumradius and area of the triangle. Students, this proof or this result is not given in your textbook, but in proving a sine rule, we will find this relation directly used in the proof. And at time, students get confused that how we got this relation, because they might have forgot or they might have not studied this result in the previous education, and they try to remember or this result or to recite at the time of writing rule. And you know that mathematics will not go with cramming, and they tend to forget this result. So to understand this result, which is rule of circumradius and area of triangle used in the sine rule, which is there in our syllabus, and very important question which will be asked for 3 marks, and if it is asked for 4 marks, that will come with one example to solve. So for that rule we need this result. Okay, this 2A and 2R can be exchanged like this. 2A will go over here and 2R will come in denominator. Okay, any of this form can be used for solving sine rule. Now we will begin with the sine rule. Fixed question for 3 marks from trigonometric equation. The statement says that in triangle ABC, with the usual notations, obviously, that is small a, small b and small c, you can see are the length of the sides. So in triangle ABC, a upon sine A is equal to b upon sine B is equal to c upon sine C is equal to 2R. Now this small a, small b and small c are the length of the sides of the triangle, and where capital A, capital B and capital C are the angle of the triangle. And this 2R, the R is circumradius of triangle ABC. By the previous result, you know what is circumradius and the relation between radius and area. Okay, so the concept about circumradius is clear in your mind. So the proof, consider triangle ABC. Now with usual notation, length of BC, which is opposite to the vertex A, is small a. Length of AC, which is opposite to vertex B, will be small b. And length of AB, which is opposite to vertex C, is small c. Now consider in this triangle ADC. For the angle C in triangle ADC, for this angle C, sin C, what is the formula for sin C? Is opposite side upon hypotenuse. Now opposite side over here is AD, upon hypotenuse is AC, which is nothing but AD upon length of AC is small b. So we got sin C is equal to AD upon B, which is nothing but AD we can write as B into sin C. For triangle ABC, area of triangle ABC is equal to half into base into height, which is equal to half into base is BC into height is AD, so which is equal to half into BC is A, and AD we got as B sin C. So we will substitute that value over here. We will transfer this 2 on left hand side. So we got 2 into area of triangle ABC is equal to AB sin C. Now we got this AB sin C as a 2 into area, okay, of triangle, okay, as we have taken perpendicular from A on BC, which is AD. If you take perpendicular from B on AC, okay, I repeat, if you take perpendicular from B on AC, you get the another direction of the triangle, okay, and in the similar manner, okay, you can prove 2 into area of triangle ABC is equal to AC sin B. You can observe AB sin C. So similarly, in similar manner, by taking altitudes or perpendicular from B on AC, perpendicular from C on AB, you can prove these two results. Triangle is remaining same, only you are going to change the direction, or you will be rotating the angle in 180 degree. You can get BC sin A. So exactly the way we have solved this, okay, you can prove these two also. Okay, now you can see the LHS of these three results are same, so you can equate right hand side. Therefore we get AB sin C is equal to AC sin B is equal to BC sin A. Now we will divide these three equations by ABC. Upon ABC, AC sin B upon ABC, and BC sin A upon ABC. Now cancelling the similar terms on in the numerator and denominator, we get, I'll write sin A first, sin A upon A remained, sin B upon AC, and AC get cancelled, sin B upon B, and sin C upon C. Okay, sin C capital, this C is small. Okay, this is our first equation that we got. Okay, so look at the proof now. We have to prove A upon sin A, B upon sin B, C upon sin C is equal to 2R. Okay, one of the part, that is, if we reciprocal this, okay, it's going to remain same. Sin A B upon sin B is equal to C upon sin C. Okay, so one of the part we got. Now we have to prove that this is equal to 2R, where R is circumradius of ABC. So now to prove each of this ratio is equal to 2R. And what is R? Circumradius of triangle ABC. Recently we have studied the result which defines the circumradius and the relation of circumradius with the area of the triangle. Okay, but now we are proving the separate rule of sine, so we have to again draw the geometry of circumradius of that triangle. Now, as the sum of three angles of a triangle is 180 degree, at least one of the angle of the triangle is not right angle. Okay, we will consider that A is that non-right angle from the triangle ABC. Okay, and draw diameter from the vertex A. For triangle ABC, we have drawn a circumcircle and we have drawn a diameter from vertex A at point P. Let the center of circle be O. Now we know that OP is the circumradius. That will be R, and diameter is equal to AP will be 2 times R. Okay, has the radius and the diameter has that relation. Now we will change the geometry of this triangle by joining CP. By doing this, to consider angle EPC in triangle ECP. Now angle ECP is inscribed in the semicircle as AP is diameter, so angle ECP is right angle. Now in this case, sin P is equal to opposite side upon hypotenuse, so opposite side is AC upon hypotenuse is AP. So AC, we know the length of AC is small b, as we have named earlier, side opposite to vertex B is small b, and AP is a diameter which is 2R. So we got sine p is equal to b upon 2r. Now consider angle ABC, major angle ABC. You can see the angle ABC and angle APC are inscribed in the same arc AC. You will find this geometrical figure similar to the previous result which we have proved for the relation between circumradius and area of triangle. So these two angles are congruent. What is the reason? The angles inscribed by same arc. So I'll write this in short. Major angle B is equal to major angle P, and for the major angle P we have got sine P is equal to B upon 2r. Okay. If angles are same, I can write as sine B is equal to sine P, which is equal to B upon 2r. I repeat, if the angles are same in the major, their sine functions are also equal. So we got sine B is equal to sine P, and which is equal to B upon 2r by this previous result. Now we will consider this sine B is equal to B upon 2r, and we will transfer the terms as per our convenience. 2r will go on left hand side, it will go in the numerator, B as it is, and sine B will come in the denominator of right hand side. We will name this 2. From 1 and 2 we get A upon sine A is equal to B upon sine B is equal to C upon sine C is equal to 2r, as this ratio is equal over here, and we got one of the ratio B upon sine B is equal to 2r. Therefore remaining two ratios are also having same value, that is 2r, and hence we are proved. Now this we have proved by using the geometry of the circumradius again over here, and then proving that one of the ratio is equal to the circumradius, the ratio of circumradius with the angle. You can directly prove this by using the previous result from over here when you got this. Okay, we will see to it how you can prove by using the previous result, but in that case you have to state that result. Okay, now let's see how can we prove this sine rule by using the previous result. Here we got 2 into area of triangle ABC is equal to AB sine C. This 2 into area of triangle ABC is also equal to AC sine B, which is also equal to BC sine A. This is capital C. The result which we have solved previously is 2 into area is equal to A into B into C upon 2R, with usual notations, A for area of triangle and R for circumradius. So over here see 2 into area of triangle ABC. I will rewrite this with the proper sequence which I required. 2 into area, if capital A stands for area over here, I'll write BC sine A is equal to AC sine B which is equal to AB sine C. Now we will replace this 2a with ABC upon 2r. A into B into C upon 2r is equal to BC sine A is equal to AC sine B is equal to AB sine C. Now we will divide whole ratio by A into B into C. When we divide, that means we multiply by 1 upon A into B into C with this, we get divide ratio by ABC, that means each term you will divide by A into B into C. Okay, so if this ABC upon 2 are divided by ABC, this ABC will get cancelled and we are remain with 1 upon 2r. BC sine A upon ABC is equal to we divide each ratio by ABC. By cancelling BC, over here cancelling AC, over here cancelling AB, we are remain with 1 upon 2r is equal to sine A upon A sine B upon B sine C upon. So here we are almost done with the result. Only we have to take a reciprocal of this ratio. Taking reciprocal, what we get? 2r is equal to A upon sine A, B upon sine B, sine C upon sine C. So this is the sine rule by using this result. But in this case, you have to state and prove this result which we have solved earlier. So either you use this result or you go by the method which is given in the textbook. Okay, anything will do. Only thing, your concept, your application should be correct. Okay, so either you use this, I'll write over here so that you will remember, state and prove. You have to, if you are using this result, you will have to state and prove this result. Okay, and then you will apply this over here. Okay, so in this gap you will have to, not that small, but you have to state and prove the result relation between circumradius and the area of triangle, and then only you can use this. So it is always better to go with the book method, but if you are comfortable with this and you are going to solve this method, it will be given correct. We will see the different forms of sine rule which we will use while solving problems. First is the usual form which we have proved, a standard form: A upon sine is equal to B upon sine B is equal to C upon sine C is equal to 2r. Okay. Second form is the taking a ratio separately with 2r, that is A upon sine A is equal to 2r. So we can write A is equal to 2r into sine A. You can easily get this by just transferring the sine C, that is denominator, on right hand side. If you consider this 2r as constant, because r is the radius for the given triangle, r is circumradius, so it is a fixed distance between 2 points, so it could be a constant. So if you consider that 2r as arbitrary constant k, we can write this as a reciprocal sine B upon B sine C upon C is equal to k. Okay, where k in this case could be 1 upon 2r. Okay, Okay, and the standard form has become a reciprocal, and 1 upon 2r we are considered as k. Taking two ratios from the standard form, you can cross multiply a into sine b is equal to b into sine a. So the cross multiplying of standard ratio will give you this. Similarly, if you take another two ratios, you get b sine c is equal to c sine b, and the third one is taking first and third ratio, a sine c is equal to c sine a. Fifth form will be, instead of using standard ratio, we will use this one. If you take a and b, that arbitrary constant length of side, ratio of length of sides, okay, a upon b is equal to sine a upon sine b. You got this? You transfer this b on left hand side and sine b on right hand side. From this ratio we get b upon c is equal to sine b upon sine c, and last one, a upon c is equal to sine a upon sine c. So these are the different forms of sine rule which we can use in the solving of problem based on sine rule.